Welcome to the afternoon session, to the first afternoon session. I hope you all enjoyed your lunch. In this session, we're going to talk about how we can make AI developers more productive. And it's a session where we have a panel at the end, and if you're interested, we are really interested in some audience questions as well. My name is Markus Weimer, and with me here is Sarah Bird. We are co-chairing this session. I come from the Azure data world, so the database world. We build databases, analytic tools, and data governance systems. And Sarah comes from Azure AI.
See if I get my mic to work here. Okay, so as Markus said, I come from Azure AI, and that is an org name for sort of a collection of AI developer tools on top of Azure. So largely this covers something that I think many people have heard of, the cognitive services, where we're taking sort of new algorithms and models and making them available to people through APIs. We also build Azure Machine Learning, which is our suite of developer tools, and we also work on knowledge mining and specifically Azure Search. So Markus and I are just going to give a little primer on, we wanted the session to be focused on what do we see as sort of the big challenges in making something that AI something that many people can develop, as opposed to right now where it's a very expert-driven sort of bespoke situation every time. And so we're going to talk a little bit about what we see in ML in practice and sort of open problems we see, and then we're going to have each of our visitors give their point of view on kind of what the future looks like, and then we can discuss that in a panel. So I'm going to briefly talk us through sort of the point of view of ML in practice as someone who's working on making sort of tools for it. So as we all know, a huge part of the story is building models. And I think for context for the rest of the things I'm going to say, I'm just going to tell you that what we've built is infrastructure that really brings together the end-to-end story of developing machine learning. We have specific tools in kind of each of these different spaces, or we work with open source tools. And I think the team has put amazing effort. I'm very proud of what we have, and it's nowhere near where we need to be. And so a lot of the comments coming forward are, context from building these different tools and working with customers on them, but also understanding that we're very far from where we need to be. So the first thing I want to say is, especially if you're coming from academia, there's an incredible focus on this step. Like, you would think that all of machine learning is just this step of building and training models. And in reality, there's a step that comes before that. You actually need to, get data and prepare it and give data to your models. And in industry, when teams are surveyed, a lot of them say they spend a lot more time on this step than they do on sort of building and training. Of course, once you've built and trained your model, there's another step, which turns out to be a whole giant nightmare as well, which is actually deploying this model and deploying this model in an application in your production needs. And so doing all of this together is a big challenge. And it turns out these really aren't the only steps. There's in fact kind of a hidden step 0, which is one that we face every day, which is helping people understand, does machine learning even work for my problem? Is this something I could use machine learning for? And then if someone tells them the answer to that is yes, how do you coax your problem into being a machine learning problem? And so this is actually the step where many, many people get stuck on before they even get to the nice chart that I showed you. But if we go back to kind of the main, technical steps as we know them, let's talk about preparing data. So it's, a lot more than just kind of getting the data and putting it in a data set, right? There's actually a pretty complex set of operations where you're trying to ingest the data, you're trying to featureize it, you're trying to join it, wrangle it, et cetera, transform it. And well, there's certainly some interesting work in this space. I think there's just huge gaps at every single one of these steps in terms of figuring out how do we make this more automatic, how do we make this more usable, how do we make it integrated? Like, how do I featureize in a way that's actually good for the particular model I'm choosing, or how do I choose a model that's good for the features? So a lot of actually bringing all of these pieces together and making them sort of intelligent and usable. The next step, and Marcus is going to talk a lot more in detail about specific problems and how we see them, but the next step, build and train. There's, of course, let me see, I don't know how to use my animations. There's also a ton here. It's a lot more than just like selecting a model and training a model. And of course, we've had a ton of innovation in helping people find the right models, helping people train models faster, and more efficiently, how to automatically tune hyperparameters. But I think this space is still kind of wide open, and an area that we care a lot about, particularly for customers, is kind of this area of AutoML, right? How do we make this a lot more accessible? There's also just the challenges of debugging and testing and understanding trade-offs for other features, not just sort of accuracy and performance, but what if I also care about bias? So there's quite a lot here. The last step, deploy. So if we want to deploy our model, there's actually quite a few steps to this, and this is where we've spent a lot of our time. You need to package the model in a way that it can actually be put in an application. You need to deploy it, and then once it's out there, it's not just, you're not done with it, right? It's actually a living, breathing thing that you need to monitor. You need to make sure it's actually doing the right thing in the application, that it doesn't change, data doesn't drift. So there's a bunch of things that need to happen there. And there's actually similar to the Mina step 0, there's actually a major step 4 at this process. Like, we spend a lot of time going through it once, but it turns out if you really want to use machine learning in production, you need to go through it over and over again in a programmatic way. And so then it turns into, how do I do this in a way that includes automated testing, automated, integration, development, running things when I get new data. And so we really want to go from something that looks less like this, and where it's one step at a time, but something where it's a living system where we're just automatically going through each of these different phases. And so this is kind of the ultimate challenge, in that this takes all of the problems at every single stage, and then we need to figure out how to solve each of them, and we need to figure out how to do them in a way that is automated. If we could solve this problem, we could also do RL a lot better, because this is one of the reasons that RL is often hard, is it is automatically closing this loop. So now I'm going to hand it over to Marcus, who's actually going to talk in very specific details about more open issues.
Thank you. So the key challenge is that machine learning models are software artifacts. They have to behave and be like software artifacts when they get deployed, right? Because we want to audit them, we want to debug them, and all of that. At the same time, they are outcomes of data processes, and data is murky and challenging and has lots of compliance issues and all of that. And that's kind of the key frustration that our users experience, is that there is kind of it's a really difficult minefield to navigate. So I'm going to go in way more text-heavy slides about some of those challenges, right? As Sarah mentioned, where basically most users fail is, can I take my business problem and phrase it as a machine learning problem? Is this a good idea, yes or no? Is there another way that would be better, right? Because if you could write software, you shouldn't use machine learning, right? We've tried this with with face detection and stuff, it didn't work, so we do machine learning. But this is a complete art. And from a research perspective, my question is, this sounds a lot like similar to software engineering in like the 80s or before, right? But then we had the Gang of Four, we had software design patterns, we figured things out, and stuff that right now is utterly boring, like building a database client, used to be hard. And what is the step function that we can build together as a community to solve this, to make standard problems addressable in a standard way? Then, of course, AutoML is an active research area in this field. If you know it's solvable by machine learning, what do you do next? Well, you want to build a pipeline. Most of the current work, very recent work notwithstanding, focuses on the question of, given a pipeline, tune the hyperparameters. In practice, I don't find that as compelling, because in many cases, carefully tuned defaults compare favorably to a hyperparameter search. So what's more challenging for users is, how do I get from domain object, or let's say a database tuple, to a feature vector? Like, automatic featureization is, I think, a very fruitful area to make people way more productive. Now, of course, this is a bit cheekily formulated, better and fewer programming languages. What I mean by that is, let's say you use TensorFlow, and you use TensorFlow before version 2. You write a Python program that evaluates to a TensorFlow program that gets interpreted by a C++ runtime that uses various hardware. And throughout that process, nice people at Google and in the TensorFlow community made sure that the thing that you called A in your Python code is still called A in the error message that the CUDA kernel throws. And sometimes it isn't. So this is clearly a problem if you have to go through 3, 4 language layers of different languages just to express your machine learning model. That's what I mean with better and fewer languages. Clearly, there is not one that we could use today. The Julia people might disagree with me on that statement. But this is an interesting area of future work in my mind. The last one is, of course, model understanding and debugging, right? What I mean by that is, we already have some works, right? Some of it came out of UW just across the lake, on understanding specific instances of a model, right? But how do I then say my predictive model told me this dimension of my feature vector is indicative of this decision? How do I relate that backwards through the feature extraction pipeline? How do I know that this particular dimension of my feature vector was actually a collection of words in my word embedding model, right? Yes, theoretically we can pipe this through, but in practice we really don't have really good tools for that. So this relationship between raw data and back to decision making is completely unsolved in my mind. Another group of open issues that I think could use some more research is this whole automation of the process, right? We have very mature, thank goodness, processes to build software, to test it, to deploy it, to pull it back, to roll it back, and they work most of the time. And I can say this because whenever they don't work, it's a major news for the day, right? When any of the big cloud providers has an outage, which happens so rarely, it is major news, which means that hundreds of times, thousands of times, it goes right before it goes wrong. We have nothing like that for the machine learning workflow. If I have a distribution drift that goes so slowly that I can't detect it as part of my data tests, if I have data tests, things fail, and they will fail in spectacular ways, and that will be terrible, and I have no way of knowing this. And we need better software here. Similarly, in the deployment area, right? Right now, the state of the art, and we do really well at this as Microsoft, is take your Python script that is your prediction engine, stick it into a Docker container, deploy it to Kubernetes. Now, if you go to a medium-sized bank with an IT department of 5, and you tell them, hey, machine learning is easy. You need a Kubernetes cluster, learn Docker, deploy this thing in Python. They look at you and say, well, but all of our software is written in Java, and that's what we know. Like, how does this work? How does not compute what you're saying, right? So there are clearly some challenges here, right? And there are some answers, right? One answer is coming from us and a couple of partners in Onyx. Another answer is in the room with Chunky and TVM. There's options here, but I don't think any of them are fully developed yet. Then, of course, performance is always an issue. It's especially an issue if you have models that then need to target many different devices. I don't know how many of you have used Microsoft Teams. Microsoft Teams has a feature where they can blur the background, right? For a machine learner, this is kind of a pretty straightforward thing. Detect the face, everything that's not the face, make that blurry. Now imagine the sheer variety of hardware this needs to work on well within latency constraints. Because you don't want choppy video just because the other person has a slow processor, right? So this is a phenomenal challenge which advanced organizations like Microsoft and our competitors can solve, clearly, but it's not something that average companies can solve. How do I get my machine learning model to have predictable performance across various hardware? Is super hard. And we see this, right? Even today, the dominant way to do things on GPUs is do it through CUDA. It's a single vendor solution. This means that we as a community haven't fully understood this problem to such a level that we can do a multi-vendor solution. Then, of course, this is a personal pet peeve of mine that I've hit personally a while ago. Once you deploy models, right, when you deploy software, the software is deterministic and a person uses it, and if they send you a bug report, that bug report is because your version of the software had the problem. In machine learning models, there are these living, breathing things that you deploy that learn from user behavior. But that user behavior is influenced by other models. You can only click on ads that you've been shown. You can only go to pages that were in the search results and all of that. And everyone in like the big online companies is very aware of this problem. I'm not aware of a really good solution that truly allows us to model this relationship between the user, the model, and the data they generate. That through a user, we generate new training data for other models. And the last thing that I wanted to highlight as a kind of a big area of problems that I see is we want to be responsible about this. Just like we got really responsible with software design, and only very rarely do we see catastrophic results in software, we want to have the same thing in our machine learning systems, right? We want to be able to go to a machine learning system and say, I want to audit this system. How does it make decisions? Now, this is challenging because I have to go from the application code, the software, to the model, to the underlying data. Now, if you try to do this in a deployed model, you might find that you don't even have that chain anymore. You no longer know what version of the software is shipping with what model trained on exactly what data, right? There's a bit of an embarrassing fact, and most data scientists say, oh, in my organization, this isn't happening. We are way better than this. But still today, this is happening, and it's a very common concern, right? Because we don't have established standards like, my software lives in Git, and I log the Git hash whenever I start my software. Done. I know exactly what version of the software is producing these decisions. For machine learning, we don't have that. We don't even have version numbers, right? For software, we have semantic version, like a.b.c. If a increments, you know all bets are off. It might be a different piece of software. In models, we don't have this. And of course, then, the flip side of doing auditing is, if it goes wrong, you need to know why. If some consequential decision went wrong, you need to be able to say, oh, did I make a poor modeling choice? Did I fold the label into my feature set by accident or something like that? Is it the data that truly suggests a certain behavior? That was, for instance, the case in the slightly racist Twitter bot that Microsoft had a while ago. The data that it was fed with by the Twitter community was pretty bad. Or is it a statistical fluke? Models are very impressive in the aggregate, but in the instance, they make terrible mistakes. Like one of the recent winners of ImageNet that misclassifies plastic turtles for assault rifles if you hold the turtle in just the right way. So there's a real problem here, right, where you can't attribute a decision to something that someone did. And that's terrifying because then you can't correct it. And I think that needs a lot of careful research from the whole community. So I hope that we hear hints at answers for some of those and maybe others that we missed when we were getting together and thinking about what do our customers really struggle with. From our panel, we have 4 distinguished speakers, starting with Zhang. He's at ETH, where he leads the DS3 lab. And I know him through his work on doing CI/CD for machine learning models and kind of bringing this model testing and unit testing a little bit closer together. He'll talk about his work there. Matej Zaria, we all know him as the creator of Spark. More recently, he's been working on MLflow, which is a thing that I'm personally quite interested in, which allows for logging of machine learning experiments and also capturing of models with some metadata. Jiangqi is currently still, I believe, a PhD student across the lake at UW, but he's going to join CMU soon as professor there. And for those of you in the room who are data scientists, you've used his work because he has been the co-creator of MXNet, of XGBoost, and TVM. So he's been quite prolific in his career so far. And lastly, we have Gustavo Alonso, who's also joining us from ETH in Switzerland. And he has a very long career. I can't really talk about all of it because really I don't remember. But the part that I got really excited about is this, and I must admit this, I only understood this last January at an event there, is why are FPGAs cool for machine learning? And that's because you can do things that are not for Neumann architectures on them, and stuff that is sequential in for Neumann architectures is not necessarily sequential in those architectures. And I hope he will share some ideas around hardware for machine learning with us. With that, I'd like to hand it over to Say as our first speaker.
Okay, so hi everyone. So in the next 7 minutes, as I promised Marcus, so I'm going to kind of summarize what we have been working on over the last 3 years. Right? So over the last 3 years, myself and my group have been actually working on like one question. Right? That is, how can we make machine learning systems more usable for non-expert users? So what do I mean by that? By non-expert users, I mean those colleagues that we have in university. They are astronomers, biologists, social scientists, people predict the weathers, right? So we try to make sure they can actually use machine learning for their own specific task. If you look at those users, right, so they are expert in their own specific domain, but they have never been through the formal process of using, they have never been through the formal training process of machine learning and computer science. By making the system usable, our goal is really try to make sure all those users can build their own machine learning applications from scratch all by themselves. So I have no idea about what the answer is, right? But let me kind of share with you a little bit about our journey and about how we think about the problem change over the last 3 years. So at the very, very beginning, right, so what we need to work on is pretty clear. Because if you look at 3 years or 4 years ago, so the system bottleneck is very clear that machine learning used to be extremely slow. If you try to get a machine on the cloud just like 4 years ago, right? So all you can get is a machine that gives you 1 to 10 teraflops. But if you look at what you can get today, you can actually easily get something, if you are doing the right floating point operation, you can get something that has 1 petaflop in a single box. And on that box, you are able to train a pretty decent neural network on ImageNet in just like 5 hours. But it wasn't the case like 3 or 4 years ago. So that is why you actually see a whole bunch of people from our community, from machine learning community, and including ourselves, really try to, like 3 or 4 years ago, try to understand how can we put together all those pretty weak boxes, and how can we speed up and scale up machine learning training process. If you look at today, right, so speed is still a huge problem. Even on a pretty small data set, like 100 gigabytes of text, right, training a machine learning model can still take weeks on cluster of GPUs. But we also start to see users who are actually not bounded by speed anymore. If you talk to biologists who only have like 100,000 images, speed is not their concern anymore as of today. So what's next? Right? Because speed is necessary for a system to be useful and to be usable, but it's not a sufficient condition. So next system bottleneck that we realize is actually about automation. That is, even if you have a system that's very, very fast, many of our users, they are still overwhelmed by a number of choices they need to make when they build a machine learning application. Even if they just want to build an image classifier on ImageNet, right? So they need to choose between all those family of models, and for each of those models, they need to tune a whole bunch of hyperparameter, either for architecture, or they need to tune hyperparameter for the training process. And what makes things worse is machine learning is an area that keeps getting updated. Every single day, there may be 10 or 20 papers that our user want to try. And this is just about the models. If you think about the end-to-end machine learning pipeline, you are actually asking a biologist to choose all the way from data denoising, feature extraction, hyperparameter tuning, model selection, model architecture search. Right? If they get lucky, they get something useful. But they are biologists. Right? So highly likely, they are going to make some wrong decision in the middle and get a model that's not even useful at all. So that is why you see a whole bunch of people actually try to focus on how to automate every single step in this process. If you look at all of the major cloud service providers, they have their own AutoML systems, and a whole bunch of startups try to focus on automation. And we also have our own small system that we can actually play with. If you look at today, right, automation is still a huge problem because like for a lot of those like different stages, we do not even understand what is a good search space, right? So not to say what is the optimal search algorithm for that stage. But we also start to see users who can actually be served relatively well by existing AutoML systems. You start to see users who can drag and drop their data set and get some machine learning back. So what's next, right? So assuming the user have a perfect AutoML system and with infinite number of GPUs, like what should we focus on as the next step of usability? So the next step, I think, in my opinion, is about things that actually beyond speed and beyond automation. If you think about speed and automation, they are actually solving something that you want the system to do on day one. You get a task, right? So on day one, you want to build a machine learning application. You get a data set. Your goal is actually try to get some model as fast as possible, right? So essentially, at this step, you care about speed. You care about automation. But your job doesn't finish after day one, right? If you really want a machine learning application to be useful to have the same quality requirement that your application need, right? So starting from day two, you are actually trying to getting a sequence of models that keep getting better and better. And on day two, you start to care about a different collection of questions. You care about how to understand your model to make sure you can debug the model and try to think about what twists I should do to get a better model. Right? You need to have a systematic way to improve the model. You need to monitor and provide get guidance from the user about what to do next. And you need to want to have a system to manage the whole workflow. But even before day one, there's something you need to do, right? Because before you start to use machine learning for your application, you kind of need to understand whether I should even start a machine learning project or not, right? So on day zero, essentially, you care about things like feasibility study, sanity check, whether I have the right amount of data or right type of data to support my machine learning application. So in our opinion, the problem for day zero and day two is actually at least equally important than the things that the user want to do on day one. And at least for us, it took us embarrassing amount of time until we realized that. It actually took us 2.5 years before we realized that day zero and day two is actually an equally important problem. So if you really focus on day zero and day two, there's a whole bunch of interesting questions that you can actually start to answer. Right? For example, on day zero, you can actually try to understand whether there's a systematic way for you to answer the question for the user that do I have the right data for this ML task. If you care about day two, you can actually start to think about how to do continuous integration and delivering for your machine learning task, how to do profiling of overfitting behavior for your machine learning task. And we are actually pretty excited about essentially this collection of problems. And some of them have papers, some of them we are still working on that. I don't have time to go into detail, but if you are interested in that, we can actually talk offline. Yeah, that's it.
So next up is Matej. Oh, you need to stay wired up. You will be back in the panel.
Yep.
Okay, so there we go. Look at that. We can manage files occasionally.
All right, thanks. So let's see. Yep, I'm Matej Zaharia, and I'm also going to talk about infrastructure for developing AI and machine learning applications. So I think the talks before really set the stage for this, because everyone's already said that even though a lot of work has gone into training performance, there are many other problems that affect our ability to build production applications. So I'm going to talk a little bit about some of what I see as the problems and some things that I'm working on. And I'm going to talk from both a research perspective and an industry perspective, because I've been spending some time in industry as well to work on some of these problems. So the first thing I wanted to start with is how building AI-powered applications is different from traditional software. And I think this then gets you to the type of systems and the types of problems you need. So let's just start by looking at that. So first of all, let's look at what the goal is when you're building the software. In traditional software, the goal is usually to meet some kind of functional specification. Like if the user presses this button, the file is deleted. If they remove someone from the event, the thing goes away from that person's calendar, whatever it is. So that's what it is. even the goal in machine learning, I think, is usually different. So in machine learning, usually it's not just a Boolean thing, does it work or not? The goal is actually to optimize some kind of metric, like let's say the accuracy or the click-through rate or whatever it is. And as a result of that, you're never really done with it. You never say, okay, we're finished with this machine learning application. You can always improve the model, and you constantly want to experiment with new techniques and see if you can make it better. If you improve that prediction accuracy by 1%, it's a huge difference in revenue, huge impact on user experience, whatever it is. So that's one difference. Second difference is what goes into the quality of your application. So in traditional software, the quality mostly depends on your code. If you wrote the code correctly and it matches the spec, you're good. And there are all these tools for looking at your code and validating it. In machine learning, the quality also depends a lot on the input data and also to some extent on other fungible things like the training method and the tuning parameters you used and so on within the algorithm. But just by definition, machine learning is programs that generalize from data. So if you put in bad training data, it's not going to give you a good result. So that's a difference as well. You got to monitor and improve your training data. And then the final thing is about debugging, how to tell if it's going wrong. So in traditional software, okay, debugging is hard, but once you notice something is going wrong, it's fairly mechanical. You get a stack trace, you turn on a profiler, whatever you do, it's a well-understood process to go through. On the other hand, in machine learning, the models are often opaque. And if I just tell you this model is mispredicting this data point, it's kind of hard to tell what's happening or how to improve it. And the data is also more complex to look at. So the big question is, okay, if these AI and data applications are going to be everywhere, what should be the infrastructure so we develop them? And hopefully I convinced you that they're qualitatively pretty different from other software. And I'm going to talk about these two perspectives. So with my academic hat on, I work in this lab, Stanford Dawn, that's focused on infrastructure for machine learning. And I'm going to talk about algorithms and abstractions to make sense of these data-driven applications. And then with my industry hat on, I spend some time at Databricks, a startup company, and we're developing this open source ML platform. And ML platforms are a concept that's well established in the tech industry now. It's a new type of system to manage the life cycle of ML applications. It's very successful, and I think it's a very good area for research as well. Like, these are super useful, and I don't see anyone writing papers about them. Okay. So let's look at this. I'm just going to talk about one example of a problem and some work we did. Obviously, I don't have too much time. So the problem I'm going to talk about is quality assurance. You've got your ML application, but these applications can fail in complex, hard to debug ways. Sorry for the overlap. I think the slides were copied and lost their format. So an example of that is these Tesla cars, multiple cars crashed into these highway lane dividers in California. It was easy to explain the behavior, and I mean, it was easy to write about what the behavior was, but it's not clear why they did that. But they did this. And another example that's well known is these gender classifiers would do very poorly for dark-skinned people because they didn't have a lot of maybe training data in that case. So these are just some examples of problems. So how can we test applications and avoid these kind of problems? And the idea we're looking at is taking software engineering techniques and basically applying them to machine learning. So, and adapting them to work with the ML training process, which involves data and optimization and stuff like that. So one project that we started is simply using assertions. This is kind of the first line of defense to monitor applications, is you have these Boolean statements. And we're trying to see what happens if you put assertions on top of the output of a machine learning application. And we noticed in a lot of cases when people have problems like the ones described here, it's actually easy to describe the problem in terms of the output of the application. And you can actually write an assertion just as a program. You don't need to do computer vision and stuff to do the assertion. So just as a simple example, we worked on video analytics, and we noticed this problem where the model detects objects on some frames and not on others, which we'll call flickering. It's clearly a problem, and you don't need to know the internals of a model to know that this behavior is probably bad if an object just disappears for one frame and comes back. So you could imagine writing an assertion that these cars shouldn't flicker in and out. And okay, maybe sometimes it's legitimate for them to do so, but definitely you don't want this to fire too often. And then we're actually looking at how to use this to improve the training process. So you can use it for monitoring. That's kind of nice, but we're especially looking at feeding this back into the training process of the model. And we found out that there are some interesting ways to use them to get a better model just based on, does it pass these assertions or not. So just actually, as other examples of assertions, we looked at various domains. There are a lot of kind of consistency constraints you can have on the output. Like, for example, LiDAR and video should give you the same answer or whatever. We tried using these in two ways. So first way is we tried using them for active learning. So if in a lot of cases, you have to request new data to be labeled. And if we use assertions to select the data that we want humans to label, we get a better score. Now, this MAP metric is kind of weird, so it looks like it's not a huge difference, but the 0.71 to 0.66 is actually a significant difference there. The other thing we looked at is weak supervision, which is you can sometimes use the assertion to fill in a guess at what the label should have been. And even though it's not a perfectly accurate label, you can also use that in your training process and get a better result. And so these are just two simple ways, but they result in basically kind of qualitatively better detection in this case. This is with the flickering assertion. You can see before and after that the model is just better at detecting these cars. So that's the assertion part. So the other thing I wanted to talk about is in the industry part. And here I wanted to say that, I'll just go here. There's basically, there are companies building hundreds of ML applications successfully. And the way they do it is using these systems called ML platforms. So some examples are Facebook's FB Learner, Uber Michelangelo, Google TFX. These are used to build hundreds of applications internally. They're very successful. And so I think this is a type of system that's important to look at, and there are a lot of cool research problems in how to set this up. And so the interesting thing now is, these have successfully accelerated machine learning in companies, but they're limited to a few algorithms in each company usually, and they're also limited to each company's infrastructure. So there are these separate groups building their own platform. So one of the things I'm involved in is this project called MLflow, which is to kind of take these ideas and build an open source and kind of open interface ML platform that just works with whatever software people are using. It's not specific, say, to Google's infrastructure or to Microsoft's or whatever else. So we launched this open source project. I probably don't have time to show you all the things in it, but it's basically got reproducible projects, experiment tracking, and also some abstractions for deploying and monitoring models. It's an open source project, and we've seen a lot of traction for it. We started this last June, and we have over 100 contributors since, including actually Microsoft's Azure ML team, RStudio, and many others. So if you want to learn about this space, we have a short paper on it, and I also just think it's a very interesting class of system to look at. So that's basically my overview. Thanks.
Thank you. Okay, next up is Jianqi. And as you notice, we are moving from like the application and developer tier closer and closer to systems for it. Okay, take it away.
Okay, can everybody hear me? Good. Hello everyone, my name is Jianqi Chen. So today I'm going to talk about my perspective of what is the past and the future of machine learning systems. So I've been working on machine learning systems for a few years now, and when we're talking machine learning systems, I think it's important to actually take a broader scope and look back into what's going on in the history of machine learning. If you look back, you'll find that actually the machine learning algorithms, we started to do research on them as early as 1960s when we invented algorithms like perceptron and GBMs, neural networks. Many of that actually get invented before the year 2000. Around year 2000, one thing happened is that the cloud revolution, actually the arrival of companies like Google and Microsoft, Facebook, and services like Wikipedia allows us to generate and cloud a large amount of data. And those data serves as a rich source for machine learning challenges. And we see challenges like Netflix challenge, ImageNet, and other challenges that really opens a new area of each of Chris modeling field. Today, most of the data sources come in a more diverse form. So you collect data from a watch, from a car, and we will need to really find ways to address this new diverse form of data. The big data really puts a huge pressure on compute, and we start to see the arrival of cloud computing that allows us to actually make use of them. And the machine learning community started to adopt GPUs around 2006. And today, GPU still is one of the main horsepower for processing machine learning workloads. And finally, we start to see a trend of more specialization in terms of hardware. So we're building hardware like TPUs, Microsoft's Catapult project, to really use specialization to push machine learning to the next stage. So if you look at machine learning or intelligent application as a whole, you cannot ignore all these factors. Machine learning model, the data, and the hardware are the three pillars that really drives the machine learning forward. And one of the most important things, though, is that there's still one missing ingredient here. And that ingredient is machine learning systems. 10 years ago, I was an undergrad intern. Actually, I worked on deep learning by then. And I have to write CUDA code for 8 months in order to put my model onto the then GTX 2080 GPU that I have. Today, I only have to write a few lines Python code. And that was really thankful to the arrival of machine learning systems. Start 2010, we start to see systems like Apache Spark and GraphLab for general purpose graph processing and data processing, scikit-learn, Caffe, XGBoost, and MaxNet, TensorFlow, and PyTorch. These are the learning systems that really enables us to be able to deploy learning ideas in a few lines of code and really help us to improve productivity of researchers. So I worked on a few of those systems in my PhD. And one of the common themes that I see in these systems are, it's really important to make those systems scalable so that really you're able to take and handle all the big data set out there, but also really make them accessible so that there are more people will be able to use it. And we already have heard talks about these perspectives in the talks that we have here. However, if you look at current learning systems, one of the things we find that's really troubling is that while we are building systems that enables machine learning, one of the untold facts is that we need to spend a lot of engineering effort to optimize those systems. And this is okay for big companies, but as a graduate student, I spent 3 years there, and I don't want to do that anymore. So the question is like, can we actually do a bit of change here? Since we are building systems that enables machine learning that are intelligent, can we use these machine learning algorithms to then come back and optimize those systems? Well, the answer is yes, and that is something that I am trying to advocate and working on in the past 3 years. So this is a new paradigm called learning-based learning system that not only uses systems to enable machine learning, but also build machine learning algorithms that optimize the systems. And as a result, we can spend less engineering effort to optimize those. So I'm going to tell you, but in particular, this system called TVM that tries to do more of automations that enables deployment of deep learning to all kinds of hardware platforms. So the problem we're trying to solve nowadays is that now we have a huge spectrum of machine learning frameworks and want to deploy them to all kinds of hardware, including your CPU, your GPU, mobile devices, FPGAs, and TPU-like platforms. And there's a huge gap between those frameworks and the hardware and the hardware platforms. So if you look at what existing frameworks do, what they are doing is that they will represent those computations in what we call high-level data flow graphs, and where each of a color node corresponds to some operation like tensor convolutions or matrix multiplication. In order to offload them into a low-level hardware device, we will need to map each of that into a low-level library. In our case, NVIDIA write a library called CUDN. The problem of this traditional approach of learning system is that for every color node here, we have to present a library core in the low-level libraries. That translates to like 3 engineers, at least there will be more than 3 engineers who spend a lot of time optimizing those colored nodes. And as you know that machine learning is an evolving field, and we will always try to add new colored node here to introduce a diversity of workloads. Or if you are a system programmer, you want to say like, I want to take some of the nodes here and I can perform operator fusion to fuse them together to give you a faster computation because you can reduce the amount of round tripping into global memory. The problem now is that this blue node no longer exists in the low-level libraries. And so what do you do? So you can ask NVIDIA to say, hey, give me this blue node. That will mean that another month or another year. Usually, actually, we did have experience asking them to add new operators, and they took them another year. Or you can hire an engineer to do that. If you multiply that by the amount of hardware backend neural support, you can imagine it's a very engineering-intensive process. So learning-based learning systems aim to replace those human-based engineering effort by a machine learning-based automatic program optimizer. I don't have time to go into details on how we do it, but I will give you a sense on why, or why do you need this approach, and what's the benefit of this approach. Intuitively, we are trying to use automated solution to compete with engineers, but usually engineers are smart, so why can't we use learning algorithm to outperform them? I'll use the benchmark example to show what could happen in here. So here we are comparing end-to-end deep learning workloads inference results where our baselines are backed by engineering optimized libraries. If you use TVM, you can find that we can actually get better performance. One takeaway is that on standard benchmarks, there is some improvement. But the most exciting thing is that there's a 3x gap in here comparing against deep learning model with human engineered version. So this is the model used by DeepMind to play Atari games. And the reason there's a 3x gap is because people care more about classifying cats versus playing games. Or in other words, the ResNet are standard benchmarks that engineers spend a lot of time optimizing on, while if you talk to your customers, most of them care about non-standard workloads. This is where machine learning and automated solution can shine because we can automate all this process. And another good news is that we can use the same solution and use it to optimize a wide spectrum of hardware backends without having to design specialized solution on them. So another interesting thing is that besides the optimization of CPU and GPUs at UW, we're also building an open source hardware solution that allows us to have an open source hardware design, ISA, and a driver stack that allows us to explore the design of new AI hardware and combine that with the TVM compiler. And we have a bunch of improvement on that. So to give you a sense on the takeaways on my take of the current and future of machine learning, most of the machine learning systems we have nowadays are trying to push for making things scalable and accessible. And this is still a very important theme nowadays. But I see that there's another interesting factor. First of all, we want to build learning systems that are more intelligent so we can automate away many of the engineering effort and we can make them adapt to more wide spectrum of hardware devices. And secondly, we want to build a full stack solution so that we can build compilers that works with new type of hardware and optimize across the stack to give you the best performance. And that's the end of my talk. Thank you.
Thank you. So let me see whether we can pull this trick with the file management one more time. Yeah, there you are. OK, that's the clicker.
OK, excellent. Thank you. And the microphone is working, right? OK, very good. So as you have seen, and Marcus mentioned earlier, the talks have been going from how to make machine learning easier for the user, platforms, now compilation, how to deal with hardware, and now we come to the end that is actually hardware. So this is what I'm going to be talking about. So I'm Gustavo Alonso from ETH, and I have been doing for quite a while now. My background is in databases, distributed system, very traditional computer science, but I have been looking into hardware for a long time. And the reason why I have been doing this is because there is something that, especially if you come from the software side of things, there is a realization that is very important that people come to. is that computers and software, and this is a discussion, I can give you a whole lecture about it, right, are very, very much tied to the von Neumann model of computing. This affects not only the architecture, obviously, because those are the computers that we have today, but more importantly, it also affects the programming languages. It affects the algorithms. It affects the way we think about computing. Now, for a long time, that has worked very well. The problem today is that this is very, very inefficient when you're dealing with amounts of data and the type of computations that are involved, especially in AI, machine learning, and all those sort of things. And they are efficient in many ways. It's not only time, and you have seen the previous talks have been mentioning computing things for machine learning, right? Takes a lot of time, but they're extremely inefficient in terms of cost, the number of resources. This is why we have the cloud. Of course, Microsoft, Google, Amazon are very happy because people need to have hundreds of machines to run these things. But this is highly inefficient. It costs a lot of energy, costs a lot of computing, and it's only that we have to resort to these infrastructures, as you have rightly pointed out, because we don't have a better solution. So if, and this is sort of the theme here, the future of work, if, as some people claim, we are going to have machine learning embedded on almost everything that we do every day, we really need to change the way we compute, because this is not going to happen with the platforms that we have today. So at this point, von Neumann, which is the guy who is there, right, I just want to say that he studied at ETH. Of course, at the time that he studied, it was in the 20s. There was no computer science. He studied chemical engineering. And he was studying on the same building where computer science is today. So it's somewhat ironic that the people in the building are trying to get rid of von Neumann. Now, when I said delivering the computation power that we need, right, will require to rethink things from the bottom up, I just want to give you, in the time that we have, and then we can discuss more during the panel, I just want to give you the basic idea of what I mean, and then give you a very briefly an example. So, at the end of the day, we are talking, and you have also mentioned this, right? We are talking about big data. And the problem with big data is that the moment that the data starts moving around in your system, doesn't matter whether it's the cloud or a single computer, even your laptop, then you already lose. This is highly inefficient. So if the data is going to have to move, and typically this is what needs to happen, then something useful needs to happen as the data moves. So in essence, you have to start thinking about computing as something where every element of the system where the data goes through or is actually sitting becomes an active component. There are many versions of this. People talk about in-network data processing and near-memory data processing, in-memory data processing, smart storage, smart networking, smart NICs. There are many versions of this. But in essence, in the future, we will have computing platforms, if we can call them this that way, where are not going to be just the traditional CPU with some storage, or even in the cloud, the data comes from the network, you take it to memory, you go through the caches, get to the registers, and eventually something useful happens. This is not the way we are actually going to compute things. Let me just give you one example. Of course, being on Microsoft, you have to mention this, which actually shows what is happening in reality. This is not just me from academia making this up. Microsoft now has these smart NICs where there is an FPGA and an ASIC where the networking part is actually implemented. The reason why they do this, there are several reasons, but the most important one is that CPUs are just too inefficient to manage at the moment the networking part that you need to have in a cloud computing platform, and then it's better off to actually put it on a smart NIC. And that saves costs for doing something else. So this is just one example. There are many others. This is also what has led Google to actually implement the TPU. Because computing these type of models becomes so expensive that, what the heck, let's just go and do a processor specialized on this. So I just want to talk for the next 2 minutes, and then I'll conclude, about a project at ETH together with my colleague, Timothy Roscoe, just to sort of give you an idea of the type of thinking that we have. So in essence, we have gone from being software people to building our own computers to try to address some of these problems. This is a machine that we call Enzian. What you have is standard cores, in this case ARM cores, 48 of them, server grade, and then we have a large FPGA. And what is interesting is that in this machine, we have actually reversed the roles of the CPU and the accelerator. So we actually have half a terabyte of memory on the FPGA, and there is only 120 gigabytes on the cores. The idea is that most of the processing is actually going to happen on the FPGA. Why? Marcus stole my pitch, right, about von Neumann, because the type of things that you can do on the FPGA is highly parallel processing on anything that moves around in the form of a stream. So this actually fits very well with machine learning. It fits very well with the cloud, for instance, where you're actually getting data either from memory or you're getting it from storage or it comes from the network. And then you can actually take advantage of the FPGA to process the data as it goes through. And then you can also use the CPU for the type of things that you can actually not accelerate or that you can actually not change because you still need to run Linux or the standard operating system, and you need to manage the whole platform. So it's the type of systems that I think in the future are going to become increasingly more interesting. And of course, I was very happy with your talk because that, of course, the challenge of these things is how do we build the whole stack. So a big part of our research is not only actually getting this machine to run, it's actually building the whole stack from the very low-level system aspects all the way to the applications so that it actually becomes easier to use these things. For instance, one of the things that we are doing for those in the room who are really interested deeply into the system side, we're implementing our own cache coherency protocol in order to explore to what extent cache coherency is a good idea in these systems. We also have very heavy networking on the other side, so we're also wanting to use this platform to explore to what extent we can actually extend cache coherency across machines in a distributed system by taking advantage of the fact that we can implement all these things on an FPGA, and we are removing a lot of the overhead of the CPU. Okay? So with that, I finished. This is actually something that is already running and operating. This is the prototype that we have. This was actually wired by hand. And by the end of the year, we will have the boards and the prototypes, and we hope that very soon we will have a cluster of 40, 50 of these machines running on ETH. The idea is to make this all open source for people to, on the system side, to actually play with it. And of course, we have people like Che and other people at ETH who are very interested in using this platform for machine learning. But anybody who has questions or want to discuss why we're doing this, I'm happy to answer now that we have the panel. Right.
Okay, that's good. All of our panelists to come up here, and Marcus is also going to sit on the panel and sort of represent another industrial point of view. I'm selfishly going to ask a question or two at the start, but then it would be great if we could be more interactive and if you could think of some questions to ask. And then I have just one that I want to ask at the end here. So the first question I have for all of you is sort of, as I was saying in my part of the talk, that I feel like we're really in the early days. We're, a long way off from where I hope that we actually get to. And I think, as was presented in sort of several of the talks, one of the big recent breakthroughs we've had is to make deep learning very accessible is, the last step was getting the GPUs and hardware that actually enabled us to train these models and make models that are usable in practice. And so my question to you is, what's the change in the ecosystem or the innovation or the research ideas that's going to result in the next big breakthrough that's going to result in a major step function change? Is it hardware again? Is it what Tianqi was sort of implying, where we should all just go meta and start generating systems that generate systems? Or what's kind of the next big thing here?
So if I just go first, because I was the last one to talk about the hardware, I think hardware is a component that you cannot avoid. Hardware has to change. I think what we have right now in machine learning comes, you have mentioned it, right, because of the advances in hardware, the advances of GPUs. In fact, machine learning is driving now the hardware industry to a very large extent. On the new generation of GPUs are no longer graph processing units, they're actually machine learning processing units. But of course, it's not enough. You need to change the way you do machine learning. We need to look at the algorithms. We understand what is in there, right? I mean, right now we use, if you want to call it, very successful, but we use very primitive forms of machine learning and treatment of the data and the way we actually process these things. That also has to change. But doing those things will require hardware because it requires a huge amount of experimentation. So you need the two things, and hardware is one requirement that without it is not going to go.
Yeah. I guess you might. So I think it's not only hardware. So if you look at success of NVIDIA, I think the main themes and main reason I still remember, like 10 years ago, for me to choose to buy a NVIDIA card is because of CUDA. Because there is a programming model that allows us to somehow, although it's harder than programming a CPU, but it's still relatively easy to program and allows people to move all those bits onto the hardware cells. There's a trend of building more and more specialized hardware, but in the meantime, it also makes the programming really hard. And I believe, besides having better hardware, it's really important to also enable more flexible software, so we will be able to move all those bits again onto this new type of hardware.
Okay, I get to say something too? Yeah, cool. I think there's, I view machine learning as it stands right now as a really, really frustrating success. Because there are areas in this world where we know the largest impact can be had, let's say the medical domain, right? If we had a giant table with everyone's medical data and their treatment and the outcome, I'm very convinced that we could create better outcomes on average for everyone if we had that table. But in society, that's not acceptable, right? We don't want to have a place where anyone can go and say, I won't hire that person because they have a high risk of heart attack in the next 3 months, right? So whatever we can do, and there are approaches like homomorphic encryption, multi-party function evaluation, all of those things from cryptography, or maybe others that can enable that domain, which I think can be the biggest impact that machine learning can have on the life of most people. I think that's the technology that we need to make the next big step function.
Yeah, I was going to answer. So, yeah, you asked, what will be the next kind of technical change that will increase the impact of machine learning. So I think there are two different ones. So first of all, if you want to make current applications better in some way, sure, it will be, research into the ML techniques and hardware. But I think if you want to see more applications and democratize machine learning, it's definitely the platform. So the stuff I talked about, the ML platforms, now mean that, in these web companies using them, there are now hundreds of application features that are powered by machine learning, whereas there used to be just one or two before. I know just in Uber Eats, for example, I think there are about 20 different machine learning models to, recommend the food to you, tell you the estimate of how long it will take to come, suggest a price, suggest a discount, all that stuff. And you can't scale to like this level of ML-powered features without a different way of developing the applications. And they're very simple models and stuff. The key is getting them to keep running well. Yeah.
Yeah, so I agree with all of this. Right? Yeah, so and just add to that, right? Like in my personal opinion, so what could lead to the next big change, right? So let me talk about one thing that I believe could cause a change, but that's not really technical. I think one thing that's going to happen that become really interesting is actually the scale essentially the scale of adaptation of machine learning, right? So think about after 5 years, if we have maybe 1,000, 10,000 real-world machine learning applications, we can put them together and really try to understand what machine learning really is and what type of abstraction we should build to support machine learning. I think that could lead to another change from the machine learning system side.
Okay, thanks everyone. A lot of you, I guess, are putting your money where your mouth is and working in the area you think would be very high impact, so that's great. Let me ask you about an area that I think none of you are really working in, but is very interesting, which is programming languages, right? There's starting to be some work in this area. What do you think is are programming languages part of the story? Is Python always going to be the primary thing? Just, I'd love to hear your thoughts on programming languages. Anyone who wants to, or everybody.
So, we start with the same order. Programming languages, of course, everything that we have said is a very important component. You need the applications, understand machine learning, you need the platforms to be able to run it, you need the compilation, you need the programming languages, and you need the hardware to run it, right? Without that. Now, programming languages is an interesting question because I think, let's ignore machine learning and hardware acceleration for a second. Programming languages became a problem the moment that we went to multi-core. This is very well known. Forget machine learning, forget hardware acceleration, because we don't know how to deal with parallel programming. It's very difficult to do it. Now, how are things going to be, or how the fact that we have a heterogeneous hardware, now we have a CPU, we have a GPU, we have an FPGA, we have a TPU, this is distributed in the cloud, well, nobody knows, right? So there are advances, is a Spark a programming language? Well, yes, no, it's a platform. I think the notion of programming language in a traditional sense is going to disappear. You're going to have things that are closest to the platforms that we are seeing, and this is where people are going to program these things. I don't think you can actually specify the full-blown complexity of the type of applications that we are developing today using a traditional programming language.
I do think that PL or even traditional PL have a role in modern machine learning. So if you look at like TensorFlow or PyTorch, many of that, or like when we're talking about like a program abstractions or API abstractions, sometimes if you alleviate that, it could be like a programming language. If you look at like TorchScript and where everybody is heading, a switch for TensorFlow, and even TVM, we have a PL group who are working on a high-level IR called Relay that they are designing. For example, what is the better type system that allows you to express those multi-dimensional tensor constraints and helps you to generate better code. And many of the wisdoms in traditional programming language might help. Another example is that doing automatic differentiations, be able to differentiate across control flows and recursions that will really enable better expressivity of a program, that will enable better workloads. Yeah.
So I basically wanted to say what Chunky just said about how we can integrate machine learning operators into the languages themselves. Another thing that comes to mind is when we talk about programming languages and machine learning, what we've discussed so far, and I don't want to kind of talk for the people after me, is about how do we make the process of machine learning itself better expressed. But in reality, there's also this problem of how do I get my model into my application, right? And applications are written in Java, .NET, and JavaScript. That's roughly the world, right? And notably, there is like almost no overlap between that and the machine learning world today, right? Machine learning models are done in R and Python, and applications are written in another language, and we are awkwardly building bridges between them, right? And it might just be that the true solution is, hey, the world needs to write all of their applications in Python, or all of machine learning needs to be done in .NET, which I would be greatly in favor of. But that, to me, is like this chasm that we have to overcome to get more people be capable of doing machine learning.
Yeah, I don't have much to add. I think Gustavo and Tianchi kind of nailed it. And I think like basically TensorFlow, PyTorch are programming languages in some sense. So yeah.
Yeah, so I think, I mean, it all depends on your audience, right? So like for the audience, like if your audience is like data scientist, I think one interesting problem is if you look at the language for data processing right now, right? So there's Python, but there's also SQL, right? Which is declarative and beautiful, right? Mm-hmm. So I think one interesting thing is after a couple of years, like we probably need to understand which components of the machine learning program should be made in a declarative way, right? Maybe we can have the concept of SQL to help our data scientists to program machine learning in a much higher level of abstraction.
Okay, great, thank you. Well, I will share this wonderful panel with all of you. What questions do you have? And we have people who will bring a microphone to you, so raise your hand if you have a question for the panel.
Thank you, great panel. One thing, I was very impressed by the work on the architecture. I believe it was called Elysium, is that?
Enzian.
Okay,
Enzian.
thank you.
It's a flower.
And I was struck by the fact that I've seen similar work at Microsoft around the, I believe, Project Brainwave is what it's called now, and they now have a deployment across Azure. And I'm curious about the state of the art of its compiler stack, because it faces the same problem that a lot of you have just addressed in terms of the complexity of the compiler stack. Is that up to the point where it is now competitive with the rest of the work? So this is sort of a Microsoft question.
So we need a Microsoft person answer.
I honestly don't know. I think it's hard still to program for FPGAs, but I'm not working in that area.
I will speak for my perception, which is slightly maybe out of date, but I think even people working on the project were underestimated early on how hard it is to create an entirely sort of new ecosystem and a new stack, and particularly for a very different type of computing technology. And so I think they've come a long way, but it is a very hard problem.
So I can only comment, I cannot comment about Microsoft, but other companies that have gone this way, right? They have have significant difficulties building the stack that they need to use these things, right? I mean, because it's not just the hardware. You need a compiler, you need the language, you need interfaces to other things, right? I mean, so you need an operating system that knows how to call these things. So you actually need to work on the whole stack, right? And that's the big challenge. But everybody recognizes that it needs to be done. Now, what is the actual state of Microsoft? That I think there are enough people here, maybe outside this room, that can actually answer that question.
But I think this is the call out to like what was so great about CUDA that I think NVIDIA has done a great job of really trying to bring their stack up to where it was actually usable. Other questions?
You had a question. A microphone?
Can we get a microphone here? Thank you.
I mean, there's a long history of a tension between performance and productivity. I mean, this panel is nominally about programmers' productivity, but you got it into performance. And the reality is that we only had one success story and many a failure. And the success story is data parallelism. And everything else, just the reality, it's been a failure. People have tried to have all kind of for example, parallelizing compilers. Where are they? We're still using MPI. So the only thing we've succeeded is longer data words. We had one success, basically. I think SIMD has been the only success in parallelism. And so part of the question is, yes, there are all kind of esoteric way to increase performance. But we have to balance the productivity versus the performance. And I think that's a tension that's not going to go away.
I will disagree. In the spirit of a panel, let me disagree. I think, yes, you are correct. At the level of one machine, AVX, SIMD, those type of things is the successful parallelism. Whether it is the best way to do it is a different question, but the cloud is parallelism. It's brute force parallelism. It's very primitive form of parallelism. But what these platforms give you, and Hadoop, Spark, MapReduce, all those sort of things, what they give you is a way to actually parallelize things at a very large scale. It's very trivial parallelism. It's for embarrassingly parallel problems. And in that regard, I agree with you. That's as far as we are.
I take your point. Embarrassing parallelism has been successful.
Right. But that's as far as we are. So I agree. I mean, we need to come up with better ways of doing this. Right?
But there has been also some progress on multi-threading, right? If you look at async await as language constructs, that makes stuff that used to be difficult very accessible to a lot of people, right? You can just say, this task may take long. I put async in front of the function and I await an answer, and I can write code as if I had the answer already. That is a complete step function change of how many people can successfully put something into a thread that they before couldn't. So we see a lot more usage of task level parallelism as well. It's not just data parallel.
So, and if I may, following up on your thing, I mean, I think one of the problems behind our inability to deal with parallelism in computer science is this von Neumann model. If you look at programming languages, the way we think about code, the way we think about algorithms is extremely sequential. We're actually the only ones doing this. So if you talk to electrical engineers, whenever they do a circuit, right? I mean, they perfectly understand everything there is active at the same time. I mean, there is nothing sequential in there, right? And they are trained in that particular way. While in computer science, we're actually trained the opposite way. We are trained to think sequentially about everything. Now that doesn't solve the problem. We need to start thinking in different ways. But I think that there is progress being made, but we are really at the beginning. I mean, think about now these data flow architectures. That is much more parallel way of thinking about programs than what we have done until now. Again, relatively simple, large granularity, but that is a step in the right direction. Now we need to turn this into compilers that are more intelligent and do better things, right? I mean, so I think, yes, that's correct. That's the problem that we need to solve, parallelism.
And if we talk about the tension in general between just productivity and performance, I mean, compilers is obviously a huge success story here, right? Most of us can't write assembly language that is as performant as their compiler could do. And so there's also just a theme around intelligent optimization. And I think there's definitely potential for us to improve performance through that kind of channel as well.
And I would say that productivity is something that people always want, as long as under the constraint that you want to get things done. The reason that people switch to GPU is that CPU is no longer possible to actually achieve the machine learning task we want. And there's a saying that nowadays machine learning scientists always train their model in 3 days, because even if you double the compute, they will try bigger models. And in that case, you will find that there will always be people who want to push the extremes and actually get more parallelism or get more specialization because there's a demand on doing so. And you cannot simply trade that for productivity, because then your job might take 6 days or like a month to complete.
Other questions?
Thanks. Hi, everyone. Great panel. I really enjoyed it. I have a question kind of towards our first speaker, I think. You mentioned something at the very beginning that your research interest was also in how to make ML usable for non-expert users. And I'm interested in that, that the people you're working with are domain experts in their various areas, but also in regards to the entirety of all of these talks, this is a complicated process with all of the infrastructure and the frameworks and the deployment and the various aspects of this process. How much of that do you think becomes a requirement for domain experts of the future? And how much of that should really be abstracted away for them? And the caveat there is maybe they don't realize that they really should be randomizing their data. Maybe they have misrepresented samples. Maybe they're deploying at a scale that they don't understand. Where do you think that trade-off lies? And maybe that's addressed to everyone as well.
Yeah, so I mean, there are two things, right? So like one thing is after maybe 5 or 10 years, what should happen, or another thing is like today or in the next 3 years, what should happen, right? So I think the next 3 years, inevitably they need to have access to some low-level details, right? For example, they need to be able to split training and testing correctly, and I cannot tell you how often they get that wrong, right? So they have a time series, they cut in the middle and just move on, right? So I mean, in the next 3 years, before we really understand what is a common design pattern for machine learning, if they want to use machine learning, they kind of need to understand a little bit about the basic requirement, and they need to like randomize the data, those type of things, right? But I think the next 3 years, they should move away from knowing what is TensorFlow, and that's a hope, right? So they need to move away from knowing what a GPU is, right? So I think that could happen in the next 3 years. If you are talking about even longer term, right? So after we understand what machine learning really is and what is the abstraction of machine learning, maybe they can, for example, maybe we can after we know the data model of machine learning, then we can do automatic split of training and testing, right? But before that, it's very hard for us to abstract that level of detail away from them, right? That's my opinion.
One thing I wanted to put here is there are a lot of application domains where you can just do stuff end-to-end where they don't have to, explicitly use machine learning. So, and there are some really successful ones. Like there are all these, kind of cognitive services. You put in some text and it tells you whether it's like offensive or whatever it is that are widely used. Another example of something that I think is a good abstraction and anyone can use is search. So think of like adding search into an application. You just install a library like Solr. It just kind of works. You don't need to know about all the information retrieval research in there. And I've also seen people do similar things with anomaly detection or prediction. There's this library called Prophet, for example, from Facebook that can extrapolate many times of time series. So I think these will, it'll be interesting to see when you can just use these versus telling them, okay, well, go take a machine learning class and like learn, what a model is, what a test set is, and all that.
Yeah, down the same line, and this might be shocking to the academics in the room, but machine learning in practice is not as rich in variance as in research. Mm-hmm. So every company on the planet has a multi-class text classification problem. Can we please just solve that once and tell them how to train it, right? That every company on the planet can sort their emails, can route their tickets, all of that, right? So that's kind of in the same way in which it goes beyond the cognitive service, it goes to the whole training pipeline, everything, right? That you can just solve once. Another thing is, and I think that's also underappreciated in the current line of work, is there are different personas that deal with data. So there's the developer persona, there's the data scientist, there's a data engineer, there's a data analyst. And in my work, I came to the shocking conclusion that they speak different languages. They encode them all in English, but they speak different languages. And it's very important for us, as at least the practitioners, to build tools that speak the language of the target audience, right? So for instance, machine learning in SQL makes sense for data analysts, makes absolutely no sense for developers. Developers want imperative code, right? Machine learning in Python makes all the sense for a data scientist, and tools in Python makes absolute sense. Doesn't make sense for a financial app developer, right? They write their stuff in Java or in C#. So translating it into the various domains is a thing that we absolutely should do, both in terms of language that they speak and in terms of application domain.
Okay, so I'm going to ask the last question, as I told you I would. But this one I'm also willing to take answers from the audience. What can those of us in industry do to help accelerate research progress in this area?
More fundings, maybe?
Funding.
Funding, yeah.
Just add money and magic will happen?
Yeah, sure.
Okay.
That's how it works.
I like that. That's easy. Anything else that you need from us?
How many from the audience who come from the university agree that funding is an important component? Please raise your hand. Okay, so you have your answers, right?
There we go.
What
Oh,
else?
that
We
was
have
an
we
easy
have
one.
data. We have customers. We have a lot of different things.
I
You
think-
have everything you need except money.
I think, well, I mean, what will be very, very useful is to actually get honest data sets and honest use cases that are separated from the hype of these things, right? I mean, so you get, all these constant stream of huge successes on this and that, and we can do this, we can do that. You never hear about the problems, the things that don't work, the things that are not perfect, right? I mean, so getting more information on what works, what doesn't, what are the problems, and so forth, that will already be very useful, so that the work that universities do becomes more relevant also for companies, right?
Counter question to that, how would you like to get that information? Because I'm part of a group that does part of that by just publishing papers on the problem and our solution so far, but what form should that take?
So there are groups that do this, there are others that don't. There are companies that publish papers, and the papers are hugely misguiding. In my group, I tell my students not to read papers from a particular company until I explain to them what the company is claiming, because it's actually not true what they're saying. So, and I know that this is being filmed, so I don't mention companies. So it depends on the groups, depends on the companies, depends on what is the setup. But I think that separating the commercial hype, the marketing hype, from the actual technical problem that you're solving, that will already be a huge step.
Yeah, I think besides like financial support, another thing I find that was very helpful, at least in my research, is that companies supporting open source from universities. And because in that way, we get contributors and actually trying to build something that our research can be directly deployed into product of the companies, and that's also another way of getting feedbacks.
Great. Any other asks? If not, then we will thank our panel for their great talks and answers in the panel. And thank you all for coming.
Thank you.